Hello and welcome back. We'll be going through the next 5 questions of the senior mock paper which I've written. Once again, if you stumble upon this for the first time and you haven't seen the earlier videos or the release of the mock paper, you can download it in the description below and take a look at the questions before I discuss them. Let's dive right into question 6. A quick note is that when you have finished the multiple choice questions and you reach question 6, it sometimes turns out to be easier than some of the multiple choice questions. It's not really in order of difficulty. So don't assume that if you're stuck on, let's say, questions 3, 4, and 5, that question 6 is automatically more difficult. That is unlikely to be true. In this case here, it is maybe a little bit more of a technical question, once again, but there isn't really too many clever steps involved. We can move over the square root and simply square both sides. Now the reason why we move it over like this is that we are not so in favor of having 2 times the square roots multiplied together, whereas here, at least we never have to multiply the square roots together. Oops, that should be a 4, not a 2. So be very careful when you're expanding things with square roots. It's quite easy to mix things up here and there. So we have got this over here and we can move it over again. We would get 7 equals to 4 times square root x minus 24. So divide by 4 and square again. So you would get x is 24 plus 7 over 4 squared. The question is asking you to give your answer in this way. Write it as an improper fraction and then sum the top and bottom. So we'll just do exactly that. So put this together, 24 times 16 is 384. And your answer is 433 plus 16, which is 449. Okay, next up to question 7. Find the product of all solutions to this equation, log base 2 of x plus 7 times of log base x of 2 equals to 9. If you are familiar with your log identities, you might quickly realize that these are reciprocals of each other. Log 2x is the reciprocal of log x of 2. One way to see this is using a change of base. If you haven't seen it in this form before, just use log base x of x over log base x of 2, which is precisely this. Now, that means if we wanted to solve this, this is kind of a quadratic equation. Right? I can let this be a, and I can let this then be 1 over a. So log base x of 2 is a, log base 2 of x is 1 over a, and now we can write the equation as 1 over a plus 7a equals to 9. Multiply both sides by a and shift things over to get 7a squared minus 9a plus 1 equals to 0. And what you hope to accomplish is to find the product of all possible values of x. But hang on a second, right? This is not factorizable down here. So we need to think about what exactly do we want. Now, this is not factorizable, but it does have 2 solutions. I don't really feel like using the quadratic formula to give me a glut of square roots. So I'll just say that suppose the solutions are a1 and a2. That means that log base x of 2 is equal to either a1 or a2, And so if I want to find x, well, I think I should just take the reciprocal and shift it back the other way, right? So it means that log base 2 of x equals to 1 over a1 or 1 over a2. So x is equal to 2 to the 1 over a1 or 2 to the 1 over a2. And the product of these two would come from adding together the exponents, 2 to the 1 over a1 plus 1 over a2. Which in turn is 2 to the power of a1 plus a2 over a1, a2. Now, this is good news because we can find the sum and product of a1, a2 since they are roots of this quadratic equation over here. Right? It tells me that the sum of roots is 9 over 7 and the product is 1 over 7. So if we were to substitute them in, 9 over 7 divided by 1 over 7 is just 9. So that gives us our answer, 2 to the power of 9, 2 to the power of 9 is equal to 512. As I was doing this substitution, I realized that maybe a better way to have substituted it is the other way around. You have saved a bit of effort if I let the thing on the left be a and the thing on the right be 1 over a instead. But it is just a slight difference. Okay, question 8. Evaluate the floor of 5 plus square root 26 cubed. This is also another classic SMO problem where you're asked to seemingly calculate something that cannot really be calculated or to estimate something that is pretty annoying to estimate, right? Because if, let's say, we did cube this, 5 plus square root 26 cubed, that's certainly possible. By using the binomial theorem, we can expand it. So you get 5 cubed, 3 times 5 squared times square root of 26, this is the next term. And then 3 times 5 times square root of 26 squared. And then square root of 26 cubed. Now this would give the slightly annoying task, right? That if we really simplified it, we would have something like 101 square root 26. And you have to really hope you estimate the square root of 26 really carefully if you want to flaw this. Because if you are not careful, you may be off by 1 decimal place and the result is already wrong. So actually, these questions are not meant to be solved just by expanding and hoping for the best in your estimation. There's this curious feature that the two things that you're given almost always tend to be really close together. And specifically, they are so close that the difference is less than 1. If square root 26 is about 5.1 is just very close to 5. Now what that allows us to do is to make use of the conjugate to help us to avoid all of the estimation frustrations. I can take the cube of the conjugate and it will be exactly the same as the cube of the original thing, except that a couple of minus signs are going to show up in exactly the places where you would like them to show up. And by exactly the places where you want them to show up, I mean that these are going to cancel off the parts with the square roots, and the parts without the square roots don't need to cancel, we can calculate them. Furthermore, since this is close, 5 and square root 26, 5 minus square root 26 cubed is going to be, well, something slightly less than 0, but more than negative 1. Right, so it is negative, but only barely so. Well, if we add them up, all we have is 2 times of the stuff we like. 5 cubed. And 3 times 5 times 26. So this is 125. And this is equal to 390. So 1030 will be the sum of these two. And notice that this is an integer, and all you have added is something between 0 and negative 1. Which means, in effect, adding this is doing the floor. So 1030 is really going to be your answer, since all you have done is taken the original thing, cut off a decimal part, and gotten an integer. That's precisely the definition of the floor function. And so we get our answer just like this. Question 9. Let theta be in the first quadrant. Determine the minimum value of 12 cosine theta plus 30 degrees, cosine theta minus 30 degrees, minus 6 cosine theta plus 99 over 4. So a few things first. 99 over 4 isn't really very important. Usually when you see something like that, it is just to make the final answer into an integer. You may also see the 30 degrees here and be very aware that it is a special angle. So it is kind of tempting to just open this up using your compound angle formula for cosine. But that may not be the best approach, because you're going to get cosines and sines multiplied together, and the result may be a little bit difficult to minimize. So instead of doing that, what we can use is our product to sum formula. The product to sum formula, or just write it here for reference, is that 2 cosine x cosine y equals to cos x plus y plus cos x minus y. So since we have that for cosine times cosine of anything, we can also apply it to theta plus 30 and theta minus 30 degrees. So our expression, you can exactly apply this to get cosine of the sum. The sum of theta plus 30 and theta minus 30 is just 2 theta. The difference between them is 60 degrees. So cosine 60 degrees. We are reasonably happy with this. The things behind, I'll just leave it first. And cosine 60 degrees is half, so that's okay. Cosine 2 theta and cosine theta, we are okay with that because we can apply the double angle formula on cosine 2 theta as well. So I'm just going to write it like this. 6 times of cos 2 theta minus cos theta plus 6 times half is 3, so you get 111 over 4. And then once you apply your double angle formula, this becomes a quadratic in terms of cosine theta. So 2 cosine squared theta minus 1 is the double angle formula for cosine. And then you can complete the square on the inside. So when you divide by 2, you would have cosine theta minus 1/4 squared minus 9/8. But really, when you have a big glut of terms like this, it's easier to just recognize that the minimum happens when cosine theta is 1/4 and put it back into the thing on top, right? Rather than working in this completing the square form, just in case we messed up one of the constants. So just put it back into here and see what we get. So 2 times 1/4 squared is 1/8 minus 1/4 minus 1 plus 1/4, and this would be equal to exactly 21. So that will be the minimum value of this expression, which is attained when cosine theta is 1/4. Okay. Finally, let's look at question 10. We have our first actual geometry question. Always the center of the circle, and we have 2 diameters. Let me highlight the diameters. These are usually very important because they give us a whole lot of goodies. Right? When you have a diameter, it means you have right angles. It also means that you get lots of radii, which gives you lots of isosceles triangles everywhere. So lots of goodies is what I'm saying. E is a point on minor arc AD, F is the intersection of CE and BD. If CF equals to FO, and DBE is 21 degrees, find AEB in degrees. Okay, so here's what we have gotten. We have got a small isosceles triangle in addition to all the other isosceles triangles that we already have. We have also got one angle which is 21 degrees, and we're supposed to find AEB. Now there are many specific ways you can do this, but generally speaking, what we're going to do is to simply angle chase around quite a little bit. There are lots of things that we can use with the isosceles triangles, the right angle from the diameters, and it doesn't really matter what you call your initial angle theta. It also doesn't really matter what order you do the angle chasing, as long as you get to everything in the end. So here's what I'll do. I have angles COF and angle FCO are equal. I'm going to call those theta. So the exterior angle here will be 2 theta. As I said, you can do this in a lot of different sequences, but what I'm going to do is quite simple. I see that this angle here is theta, so this also is theta by your angles in the same segment. And so now in this isosceles triangle, you have got theta, 21 plus theta, and this angle would also be 21 plus theta. So we can find theta from here immediately, right? So theta plus 2 times of 21 degrees plus theta is 180. And so theta would be equal to 46 degrees. So we're supposed to find angle AEB. AEB is just half of angle theta, as we can see, right? Because AEB will be half of this angle theta here. So we are done effectively, even faster than we might have thought. So this is a typical circle geometry question where if you can't actually start finding angles one by one just yet, it is also a possibility to just call one of the angles theta and just move through the whole diagram. With two diameters, an isosceles triangle, it is not surprising that there is ample information for us to find angle theta no matter what we chose to call theta at the very start. Alright, so that's it for this video. Thanks for watching. Please subscribe if you would like to keep track of the rest of the coming videos, and feel free to let me know of any questions or comments in the discussion below. Thanks again, and see you next time.